Did you get it? I will begin with a word of prayer. What's that?
I was just saying, I watched the video for Friday, and you insulted everyone who wasn't here.
I did that, yes.
I watched the video, so I know.
That's good. That's good. What was my insult? I forgot my insult now.
You said all the good students.
Oh, all the good students. That's right. That's right. That's right. So I guess I was really attempting to insult people who also don't watch, but I don't know. How many people? 1, 2, 3, 7, 8, 9, 10. Well, I guess we have two-thirds attendance today. That's a win, I suppose. I will begin with a word of prayer. Dear Father, we thank you for this day. Again, Lord, I thank you for these students, even the ones that are not here. That's true. Just help them to work on this course because they need to pass. And I just pray that you'd give us guidance today, help us to understand what we're doing, Lord. In your name I pray. Amen. I got a couple of examples for you guys. Let's see here. Example 1. Suppose you had f of x equals to the natural log of 2 plus x cubed. I want to find the Maclaurin series for this. Am I right? So you could start differentiating and try to apply Taylor's theorem directly. That would get old very fast. So this is one of those ones where geometric series is the way to go. So what we do is we differentiate. Differentiating it gives us 3x squared over 2 plus x cubed by the chain rule, right? And then you got to use your imagination a little bit. This is 3 halves x squared over 1 plus x cubed over 2, right? The reason I write it that way is because now I can use the geometric series result, right? Geometric series says that this is the sum n equals 0 to infinity of 3 halves x squared minus x cubed over 2 to the n power. Now, some students make a mistake here of trying to then integrate that to get back, but that doesn't usually happen too much. I mean, what I'm trying to get at here is we want to simplify this before we try to get back to the function, right? So let's see here, simplifying, this gives us the sum n equals 0 to infinity of 3 over 2 to the n plus 1 times minus 1 to the n times x to the 3n. All right. So there you go. We found the power series, not for the function, but for its derivative. And, here. This was the function I wrote, but what I meant was plus pi. So if you don't mind, I'm going to add a pi. Did that change the derivative? It did not. All right. So now, to get back my function, f of x is equal to the integral of df dx, right? Which is some constant. And then I term by term integrate that, which gives me the sum, n equals 0 to infinity, right? 3 over 2 to the n plus 1 times minus 1 to the n times x to the 3n plus 1 divided by 3n plus 1. This is the term by term integration theorem. Then what? Well, allegedly, this is equal to my function, right? So if I plug in x equals to 0, what's that give me? F of 0 is what? It's natural log of 2 plus pi, right? But what's that equal to? C plus the sum of 0. And I say, is that a reasonable step? I mean, you got to think through this. If you don't think through it, it'll get you in trouble eventually. n equals 0 gives me what here? X, right? So the lowest order term is x. Then I've got like a x to the fourth and so forth. All of those are 0. When I evaluate at 0, the series is 0. So lo and behold, I get c is equal to pi plus the natural log of 2. And so my answer is natural log of 2 plus x cubed plus pi has the following Maclaurin expansion. It has this, oh, I'm sorry, can't do math. It has pi plus the natural log of 2 plus the summation n equals 0 to infinity of 3 times minus 1 to the n divided by 2 to the n plus 1 times 3 to the n plus 1 times x to the power 3n plus 1. There you go.
The denominator is 3n plus 1, not root the n plus 1, correct?
Yeah, 3n plus 1. Yeah, not 3 to the n. No, no, no. So any questions about this one? Yeah.
You plugged in, the sum of the geometric up towards the top, the sum of the geometric series, you use like the form of the geometric to get that, right?
Right. So going from here to here,
Yeah.
a is 3/2 x squared, and r is minus x cubed over 2.
Okay. Now going from there to the next step, where did the negative x, where did divided by 2 go?
So this gives me 2 to the n, right? So I got 2 to the n times 2, which is 2 to the n plus 1.
Oh, okay.
And then minus x cubed to the n is minus 1 to the n times x cubed to the n, but x cubed to the n is x to the 3n.
Okay, I don't know if I'm going to do that, but I did.
All right? Other questions? Where'd the what? The x squared. Oh, goodness gracious, come on. Oh, man. Well, it's good that you couldn't do it because it was wrong. Right? So if you should have, everything I just told you, I was telling you about this factor, right? I completely ignored that, which does what? What does it do? What's the difference? I mean, this is right, except that it's missing my plus 2. That's kind of important. So when we integrate term by term, we get what? Not 3n plus 1, but 3n plus 3, right? This is a 3n plus 3.
And did you put it in that form? Because it looks like alternating a series, kind of with the negative 1, or is it still geometric? Did you put it in that form to make it look more like?
Well, I put it in the, I mean, okay, so, a Maclaurin series has the form a to the n, x to the n, right? So I have to write it in this format. I mean, the x has to be by its lonesome, and everything else going on has to be put to the side. Otherwise, it's technically not a Maclaurin series. All right, let me follow through that. That puts a 3 here, right? And it puts a 3 up here, too. Sorry about that. So you don't back off your question so easily, you know? Whoa, that was close. Now this one here, again, find the Maclaurin series for that. What would happen if we differentiated that function? You get something over a cube, right? So we should do what? If we integrate this, then we'll get to like 1 over a reciprocal power, right? Which means we can do geometric to the integral of this function. So what's the integral? Yeah, I'm going to... So are you making a u substitution?
Yeah.
Okay, I'll write it out just because I think that I'm going to get in trouble if I don't. U equals x plus 4, so this is equal to the integral of 2 du over u squared, which is minus 2 over u. So what did you give me? You gave me minus 2 over x plus 4?
Yes.
Plus a constant? Very good. Now, the reason that that's interesting, of course, is because after we do that, we're almost ready to do geometric, right? What's the wrinkle? The thing I have underlined. I can't do geometric 2 yet because there's a 4, right? So we need to factor that 4 out. If we factor the 4 out, then we can use the geometric series result to expand this thing. So the integral f of x dx is equal to minus 2 over 4 divided by 1 plus x divided by 4, plus that constant, right? Does this make sense? Do you understand why I'm doing what I'm doing? Why don't we just apply Taylor's theorem directly and just differentiate this thing all until we see a pattern? Because that would be unpleasant, right? So we want a way around direct application of Taylor's theorem, and geometric series is the way to go. These are standard calculations to get around it. And these are not exponential sign or cosine anything of the standard functions, so like it's pretty much the way to go here. All right, so that's minus 1/2. Well, fine, let me get to it. By geometric series, this is the sum, n equals 0 to infinity of minus 1/2 times minus x divided by 4 to the n power. I'll put the constant. Let me put the constant in front. All right. Now we can clean that. It's not yet a Maclaurin series, and even so, it's not what we're looking for either, is it? Because this is. I'm going to pull that minus out if you don't mind. Let's see here, sum n equals 0 to infinity 1 over 2 times 4 to the n times minus 1 to the n times x to the power n. Yes?
Wouldn't it be easy to undo the integration? Wouldn't it be easier to differentiate it with the x minus over 4 to the n power?
But the thing is, I don't know if that's valid. I know that term-by-term differentiation and integration of power series makes sense. However, if I start doing term-by-term differentiation and integration of other things, we can get into trouble. It's important to rewrite it as the coefficient times x to the n before I do the term-by-term integration or differentiation. That we have a theorem which says that you can do term-by-term differentiation or integration of a power series. This is not a power series. It becomes a power series once you write it as coefficients times x to the power n. Before that, it's just something else that shall remain nameless. But anyway, does everyone agree with the, so I pulled the minus out, I kept the 2 inside, I got a 4 to the n. I got a minus 1 to the n. Are we good? Okay. Now, this, of course, is not what we're after, but what we want is f of x. F of x, on the other hand, is d dx of what? The integral of f of x dx, right? Which, so this time the constant doesn't matter. It just differentiates to 0, and we're left with minus the sum n equals 0 to infinity of minus 1 to the n over 2 times 4 to the n. We could simplify that. N x to the n minus 1. Now also, you notice here that this isn't tricky like the one we did last time with the x to the power 2n. Remember that one was a little bit fussy in terms of whether or not I can change the lower bound. Here I can definitely change the lower bound to 1 because 0 is 0. Yeah. All right, finally let me clean things up here just a bit. This is the sum, n equals 1 to infinity of minus 1 to the n plus 1 divided by 2 to the 2n plus 1, and I can put an n upstairs, times n times x to the power n minus 1. That's probably a good answer. Notice that 4 to the n is 2 to the 2 to the n, which is 2 to the 2n. So that's why 2 times 4 to the n is 2 to the 2n plus 1. Does that make sense?
Why is that minus 1 to the n plus 1?
I absorb the minus outside, inside. Yeah. One more example for you guys today, then I'll spend the rest of the time on your homework questions. Example 3. Find Maclaurin series for f of x equal to x cubed sine x plus the cosine of x. So this one here, obviously not geometric, right? This one we're just going to use the known Maclaurin expansions and work it out. So here, let me make this more exciting. 3 to the x, 7x there. Now it's properly exciting. Yes, there you go. I need to do that because I think we need to talk more about those kinds of calculations. So let's do it. All right, so what we do is we leave our x cubed out front. This is what? This is the sum, n equals 0 to infinity, minus 1 to the n over 2n plus 1 factorial times 7x to the 2n plus 1 plus the sum, n equals 0 to infinity, minus 1 to the n divided by 2n parentheses factorial 3x to the power 2n. All right, so what am I using? I'm using the known Maclaurin expansions for sine and cosine, which we should memorize if we haven't already. You'd like to know those even past this course. Like when you take differential equations, it's important to know these. So let's see here. I'll state them in terms of u. If we have sine of u, that works out to the sum, n equals 0 to infinity, minus 1 to the n, divided by 2n plus 1 factorial, u to the power 2n plus 1. On the other hand, cosine of u is the sum n equals 0 to infinity, minus 1 to the n, u to the 2n over 2n plus 2n factorial. So just odd terms, just even terms, and they're both alternating. So, you know, just to, this one, I had what? I had u equal to 7x. This one over here, I put u equals to 3x. That was the substitution I made into the known Maclaurin expansions for sine and cosine respective. Any questions about this? So now, I'm going to take my medicine here a little bit and clean things up. This is the sum, n equals 0 to infinity, minus 1 to the n, 7 to the 2n plus 1, divided by 2n plus 1 factorial, x to the power 2n plus 4, plus the sum, n equals 0 to infinity, minus 1 to the n, times 3 to the 2n over 2n factorial, x to the power 2n. Now let me point out something. We could rewrite this as, so let's see, this starts where? This starts at x to the 4th, right? And this one starts where? Yeah, x to the 0 actually, right? So if we want to combine these two, what we're going to need to do is we're going to need to peel off the 0th and the x squared terms from the latter one. In other words, what I can do is I can peel off, well, let me just write it this way. This is the sum k equals, I'm going to say 2 to infinity, all right? And what I want to do is make a 2n plus 4 equals 2k substitution. So look at that. When n is equal to 0, what's k equal to? If n equals 0, k equals what under my 2, right? So, and so on the other hand, this gives me like 2n plus 1 equals what? 2k minus 3, I think. And how is n? What's n as it relates to k? N equals to what? K minus 2, right? So let's make the substitution. What we got here? We've got minus 1 to the k minus 2, 7 to the power 2k minus 3. What's 2n plus 1 in terms of k? Oh, that's 2k minus 3. So 2k minus 3, 2k minus 3 factorial. Finally, x to the 2k. And then over here, I'm going to switch this over to k's as well. Sum k equals 0 to infinity, minus 1 to the k, 3 to the 2k over 2k factorial, x to the 2k. Now the reason I did this was so that I can add these two series. They do overlap, so my job is not done until I combine them where they overlap, right? And these overlap most places because they're just evens, right? And as I was saying, I should peel off the 0th and the second order one. So going back to here, the 0th is 1, and the second order one is minus 1/2. Well, it's minus 9/2 x squared These are the first two terms in the cosine of 3x. Cosine of 3x is, 1 minus 1/2 u squared, So the 1 minus 1/2 u squared term is exactly 1 minus 9/2 x squared. That's the part of the ladder series which is an oddball, right? I mean, the other one starts at power 4. This one starts at power 0. Here's the two sort of odd men out. And then I've got a common sum. Sum k equals to 2 to infinity. And then you just add things here. So big parentheses, minus 1 to the k minus 2, 7 to the 2k minus 3, divided by 2k minus 3 factorial. That's my first coefficient. And then plus minus 1 to the k, 3 to the power 2k, divided by 2k factorial, close parentheses, all x to the power 2k. And there you go. That would be the Maclaurin series for this guy. So those are my examples for you guys today. I assume you have homework questions in time that remains. Yeah.
We look at problem 255. It's one of your original.
250 problem, one of my original problems. Oh, you have it. That's good. I think my computer may have just died. Did you had a question too? Oh no. Okay. So before I erase this stupidly and forget to point out something, what's the difference between example 1 and example 2? These are both geometric series technique problems, right? Neither of them apply. Neither of them, we don't use the geometric series directly on either one of these, right? The point of these examples is you have to know enough about calculus to realize, wait a second, if I differentiate that function, it looks like the geometric series result, right? Or this one, wait a minute, if I integrate the function, it looks like something I can do geometric series to. And then you have to have the thought process, well, after I do that, I have to undo what I did, right? So to undo differentiation, we integrate. To undo integration, we differentiate because they're inverse processes. And that's basically the idea. There are other more awful problems, like what if you had 2 over 4 plus x cubed? How would you do that? Yeah, you'd integrate twice, do geometric, and then differentiate twice to get back. But if you understand how to do this, you understand how to do that. So I'm usually happy to just test on this. But back before I lost the will of fire, I used to test on the double differentiation or double integration ones. Let's see here. Okay, where was I? So 255, you say? So I gave you guys f of x, sum, c sub n, 2x minus 1 to the n equals 0 to infinity. What do we know about this? The IOC interval of convergence is, I lost it, minus 2 to b. B is not included. My parenthetical remark is messing with me. I don't think it matters.
Okay.
So that this says interval of convergence minus 2 to b. My question is what's the value of, what's b? Find b. Anybody get this one? Yeah?
Would this be fine?
Cn are not given. So we cannot use geometric series, sine, exponential, cosh, sinh, anything. You don't know what the coefficients are. All you have to work with is just the basic structure theorems of power series. Things we talked about like the first day. What's the domain of a power series look like? And there's part of the problem already, right? See, Josh, I've been fussing that this is not a power series, right? So what do I mean when I say that this has interval of convergence? I mean the corresponding power series has that interval of convergence, to be clear. So the corresponding power series is what? How about that is what? That's 2 times x minus 1/2, right? Agree? So the power series here, if you do the algebra, is c to the n, 2 to the n, x minus 1/2 to the n, right? There we go. Now that's an honest to goodness power series, right? So what are possible domains for this function? What do they look like? They could look like this, right? They could be just half. They could be just a half. They could be the whole real line. The domain could be what? It could be like minus 1/2, minus r, minus what? Oh, minus a half, plus a half rather. Half minus r, half plus r, right? And you can have the same things like this, or like that, or like that. Right? Radius equal to 0, radius equal to infinity, radius equal to the radius. Those are the possible domains. These are the possible IOCs. Right? So where do we fit? What's that? Yeah, we're in one of the last 4 cases, right? We're in the closed on the left side, open on the right side case. So what does that tell you? Do you know what, you know what the center is, it's half, right?
So the equation is negative 2 equals 1 half minus r, then just solve for r then.
Uh-huh. Yeah. That's half of it. So what's r equal to? I can draw a picture on the number line. That's maybe the best way to think about this. Here's the center. 1/2 is x naught, right? And minus 2 is included, right? But the domain for the power series, if it's finite, symmetric about the center, ignoring the endpoints, of course. So how far is that? What's this distance? Distance between 1/2 and minus 2. Five halves, right? Very good. I was a little bit worried there for a second. So then the same goes for this side, right? over here is that b we're looking for. So what's b equal to? Not 5/2, no.
Oh, sorry. 1/2 plus 5/2, which is 3.
You said it. That's right. Right. B should be 3. I seem to have worked your problem for you. I'm sorry about that. No worries. The thought process is important here, though. What's the point of this problem? Is to try to get you to think about what does the interval of convergence look like, right? What kind of information can you extract from partial information about a power series? Here's another one. If I have power series and it's centered at 2, and I get that 3 is a place where, power series centered at 2 converges, then what can I say? What does it tell me if I know 3 is a point of convergence? What can I say for sure just from this data alone? What am I forced to admit about the function? Because of the way the domain of, because of the way the interval of convergence works, I'm forced to say that this right here, the IOC includes this. Now, I can't say anything more, right? It might go beyond that. I don't know, without more information, right? Anyway. There's a lot you can say from the fact that these are the possibilities. Other questions, other questions? So the reason I changed the lower bound over here was because I couldn't add them in their original form. Like this and this do not match. So I either can make this ugly and make it look like that, or I can make this pretty and make it look like that. But in so doing, I have to take account of the bound changing as well. See, because when n equals to 0, this is actually equal to 4, right? So when I put 2k here, that has to start at 2 because 2 times 2 is 4. So yeah, I have to think through it. But getting back to your question, it's to make them look the same because I have to have them look the same in terms of their, how the power is formulated before I can actually add the series. That's the rule.
So why did you change lower bound on that one?
This one here? That one was because I had this n. So n equals 0, it was just 0 there. I was just dropping 0. Different animal altogether there. Whew, we asked that just in time. That'd been a second later. that was close. Let's hear problem 266.
This actually seems relevant given the example we've done thus far.
Okay. Yowzers. Goodness gracious, we haven't done anything quite like this. Integral of the natural log of 1 minus t over t dt. This is the function. And we are supposed to find the power series centered at zeros via the geometric series technique. So yeah. What would you do here?
Differentiate first and then the integral. Because that's what I tried.
Yeah. Yeah. I mean, I don't know if that helps, though. Well, you said it didn't help, right?
No.
So there you go. this integration, see, I think this one here, now I could be wrong, but one way I think to do this is to look at log of 1 minus t separately. If I look at log of 1 minus t separately, then I can see that this has dg dt 1 over, well, minus 1 over 1 minus t, right? And then that is the sum, well, minus the sum of t to the n equals 0 to infinity.
That's it. That's nice.
And so therefore, therefore g of t is some constant plus, well, minus rather, the sum t to the n plus 1 divided by n plus 1, n equals 0 to infinity. Now, on the other hand, that's equal to the natural log of 1 minus t. So I think if we put t equal to 0, we get that the constant's 0. Log of 1 is 0. I think the constant's 0. So what then? So then, what's the log of 1 minus t over t equal to? Right. So when we can divide everything in the series by t, and that does what? I think what you just said, that would be t to the n over n plus 1. So at that point, what you do is you just say, okay, well, I found a nice series expansion. So it's not by direct geometric series. It's kind of indirect application. So this is a power series for the integrand. So just put that up in there, and then just do term-by-term integration. That should get you the power series. Yeah. 266, you say? 266. And this is a problem from the dark heart of my imagination, you said, but I'm sure I copied it down from some book somewhere. But
Okay. That makes a lot more sense, splitting it up like that. We've done a few examples like that. But
yeah, I mean, I was about to try to integrate by parts or something, or do something dumb. But and there's probably another way to do it, where you could just do this integral directly.
But who wants to do that?
I don't. It's unpleasant. Yeah. Yes? 252. If Nathaniel will let me borrow his paper.
Yeah, go ahead.
Hey. So you got 1 plus x plus 1/2 x squared plus 1/6 x cubed. And we're multiplying that by 1 plus 2x plus 2x squared plus 4/3 x cubed plus. So, I mean, what's your question about it? What's the question? What's the question about this one? So what did you guys get?
You just multiply it out.
Right, the way we multiply series is order by order. I'll get you started. 1. See? Don't say I didn't never give you anything. What's next? Linear terms, right? So for linear terms, what we got? We've got this times that, right? But what else do we have? So how many x's do we have? 3x, right? Is there any other possible way to get x? There is not. X squared. How many x squareds do you got? 1? Is that right? So yeah, that times that. We've got this times this. And then we've got this times this. There's those 3 possible products that go together to make the x squared terms. How many you got? 2 plus 2 plus 2 plus 2 plus, looks like a half. What's 2 plus 2 plus a half? It's 4 plus a half. What's 4 plus a half? 4 plus a half? 4 and a half is of course true, but useless. So that would be 9 halves. 9 halves. 9 halves x squared. Or, if you look at it as I prefer to look at it, this is 1/2 of 3x quantity squared. What's the quartic term?
1 over 3 factorial times 1 over 3x cubed.
Nathaniel forecasts that the next term is 1 over 3 factorial times 3x cubed. To verify that, we should calculate that there is 27 over 27 sixths, the x cubed terms rather. No, I said quartic, that's wrong. So, so you got this one times that one. You've got this one times this one. You've got this one times this one. You've got this one times that one. That gives us a sixth plus 1 plus 2 plus 4/3, which is 27 sixths. I didn't work it out. I'm just saying it must work out to that. Yes?
I think we're up on time, but I didn't get to ask you the one I told you I would ask you.
Oh, I guess we'll have to wait till tomorrow then. But so can you explain this? Yeah.
It's e to the 2x. Sorry, e to the x to the 2x.
So you've figured out the secret to my problem. This is e to the x. This is e to the 2x. This is shockingly e to the 3x. So you've proved this particular law of exponents by multiplying series. Congratulations.
Well, I wasn't trying to be cute when I said 4.5.
No, I know. It's just, but like 4.5, it's something we teach children only to like waste their time, right? Because like, 4.5 is really dangerous. 4.5. So you multiply by 2, right? And you get 8.
Out of the top,
Or 8.
multiply the number on the side of the
Yeah, it's just, I mean, if we said 4 plus a half, or we get 8 over 2 maybe, or something like that. I mean, I don't know how. There's so many opportunities for misinterpreting 4.5, right? Mixed numbers are perilous when it comes to algebra. It's very dangerous. So we'll have to come back to your problem tomorrow. First thing, okay? Joshua?
Yeah.
Yeah. Okay. Which